to the design patterns. I think then that gets more interesting because it talks now about it talks about design patterns. What is a design pattern or coding pattern in our case, or programming idiom? That you have repeating recurring problems in blockchain-based system engineering or Ethereum-based programming. And now I want to show you how we solve these recurring problems in the best possible way, and what are proven solutions to these problems. And sometimes it's the case there are multiple solutions, and in these cases, design patterns would tell about the disadvantages and advantage of these different solutions. So the consequences in the positive sense and also the negative consequences if you apply this pattern. And as usual, these patterns often have then a name. For example, the name of an oracle is something which is well known, and we talk about these names. Okay, first we start with so-called programming idioms, which are more or less repetitive ways of solving a problem at the programming level. Yeah, there's not much design involved, and therefore the first thing we already talked a lot about are these Solidity idioms for coding problems. Yeah, in our case, these are access control idioms. Yeah, for example, programming are language-specific patterns for recurring program problems. Yeah, for example, if you iterate over a collection, there's always a standard way how to iterate over collections, or if you want to do exception handling, how to do this in a safe way, etc. The Solidity, the first one what we want to cover is the access restriction idiom. And again, we would say, okay, what's the problem? Who are the participants? And what's the applicability? In our case, so since each contract is publicly accessible, we want to make sure that not all functions are public and can be called, but we want to have also access restriction. Yeah, and access restriction is very important because a misconfigured access restriction then has a huge potential for a lot of money loss in this case. Not only for programming error, but also loss of life, even and money, if you have mission critical systems. So the participants are entities that call a publicly accessible function in a smart contract, and you have a smart contract which you want to protect. And let's say when would you use it? Yeah, obviously, if you want to protect it from an unauthorized call, typical examples of such things would be a self-destruct function, that not everybody should allow your contract to be self-destructed, but maybe only you. Or you have a minting operation, which more or less creates new tokens. Okay, so as we have seen it, the idea is that you have so-called ownable contracts. If you want to restrict the count to one owner or one owning party, and that is done with these function modifiers that we have, for example, here the modifier, in our case, only owner, which I think nicely expresses what is the goal, that only the owner should execute a function, only the owner of a contract should execute functions on that contract, and it's implemented by looking at the sender object and making sure that the sender object is the owner. Yeah, so you don't look at the transaction origin, but you look at the message sender, and the message sender should be the owner of the contract. And in order to know who is the owner of the contract, you have to now define a constructor, and as part of the constructor, you then define the owner to be the sender, message sender of the initial constructor call. Yeah. And therefore, the person that created the contract is then the owner automatically. And you need a local variable, and the local variable is of type address, because the owner could either be an externally owned address or it could be another contract. So that's more or less the pattern, which more or less is very repetitive, and you should closely follow this. And then, for example, here we use it. We would say, for example, transfer ownership to a new owner would be implemented by restricting access to the current owner. And if the current owner executes these functions, you want to make sure that the new owner is not zero address, yeah, that it's not a null pointer, which would then undermine your access control and make it unusable, but you want to make sure that the new owner is an existing wallet address. And then after we have checked this, we can then change automatically the new owner. So the new owner, which you get as an argument, as the new owner of the contract. Okay. So the idea is also you could have a function renounce ownership, which can be called by the current owner, and which would more or less essentially allow only the current owner to set the address to 0, and you make it in a different operation so that you don't do this by accident, which would more or less say, okay, I'm no longer responsible for this code. I don't want to have any rights anymore on this contract. Okay, the second one is the secure ether transfer idiom. I think that might be new to you because typically in your programming language you don't move money around, and moving money around is a side effect operation, so therefore it also is a little bit dangerous. Yeah. So what's now the problem? If you send ether to another account, that you have to issue a transaction or message to the receiver. And now there could be a problem. If the receiver is a contract account, it is possible to let the transaction intentionally fail. For example, when the fallback function of the receiving contract throws an exception. Yeah, so typically, if somebody sends you money, you would assume a contract which gets money from me. What would be a good reason for this contract to reject the money? Yeah, that would be a naive assumption. So yeah, if you go to a bar and you say, I have 100 euro, who wants to get it? You would not expect that people say, I don't take your money. Yeah. So therefore, typically people don't think about it that the transfer could, the receiving contract could reject it. Yeah. And rejecting would be easy because you would override the fallback function. And in the fallback function would say, maybe if the sender is Peter, then it should throw an exception. You can write arbitrary code, which is called if you get a money transfer. Okay, so in order to avoid this problem, there is now a pattern how to do this, which I talked to you, and the participants obviously are those people which want to receive either by issuing a withdraw operation, and you have a smart contract which wants to keep track of all account balances. Yeah. So therefore, whenever you want to transfer money to somebody else, you should apply this secure ether transfer idiom. Okay, now let's look at an example. I also had to read it a little bit more carefully when I prepared for this lecture. So the idea is as follows. We have now an auction, which is called a bad auction. And the idea of this auction, and not the bad auction, is that you have now an auction where people bid a certain amount of money. Yeah? So therefore, the idea is that I say bid is a payable function. So in order to call bid, I have to equip my transaction with money. And the idea is now that I don't pass this amount which I'm bidding around simply as a value and say I'm willing to pay 5 euro, but you actually pass along the 5 euro. Yeah? So that's, I think, the way you have to think about smart contracts, that they can also get money as an argument. Yeah? So therefore, you don't look at the argument here and say he bids 5 euro, but you have to also put the money on the table. Yeah? Therefore, you have to now pass in the value as the message object. Yeah? So you have to really now have this value passed in with the message. And then the idea is now that you, as the auction, look at how much money is in this message. And if this money is higher than the highest bid or equal to the highest bid, you could debate whether this is a good idea to have it greater or equal. But now this is how it's written. But that's not the problem. You want to say the highest bidder, the latest bidder now gets, if the highest bidder is not equal to 0, so it's not an invalid address, you want to transfer the highest bid to the highest bidder. Yeah, so therefore the idea is now that if you have bids, you take the money and you more or less keep it. Yeah, so therefore here you would say the highest bidder is the message sender and the highest bid is the message value. But if there was previously a highest bidder, you want to take the money you want to transfer back the money you got from the previous bidder to the previous bidder. Yeah, that's more or less the idea of this bad auction. Yeah, yeah, and I do hope that it's clear that this is only executed once you have a highest bidder. Yeah, if there was no previous highest bidder, you don't have to do this. Yeah, so therefore this condition here, there has been a previous highest bidder. Okay, and therefore you would say, okay, now the person bids, and then there comes a higher bid, and then you want to give the initial person the money back, and therefore you do this highest bidder dot transfer. But now, if you look more closely, what could happen is now that this highest bidder could reject the money. Yeah, so therefore you would say he's happy to get the money back because there's a new highest bidder, but he would say, I read your code, and if I now would reject the money, your code would fail here, and these statements would not be executed. So therefore, for all eternity, I would stay the highest bidder. Yeah, so that's more or less the idea, that if you would write a contract which wants to play a bad game with your bad auction code, you would bid as low as possible, with low value very early on, and then whenever you want to, the auction gives you back money, you will say, no, don't take the money, and then no further bids could be created here. Yeah, because that's the only way new bids could come in, and all of these new bids would fail. Yeah. So therefore, you have to fix this problem. And I think the basic idea is that you look at the title. It's the secure ether transfer. So therefore, you now turn the activity around. You would not say, I actively give you the money, but I allow you to take the money. Yeah. So therefore, the idea, instead of pushing money into some other's wallet, and they wouldn't like to do it, you say, okay, I now allow you to take your money. Yeah. So that's more or less this secure transfer that you, more often than not, if you want to combine a money transfer and some bookkeeping, you don't do them in one transaction, but you simply say to do bookkeeping operations, you would say, okay, he's now allowed to get the money back, and you update it, but then in a different transaction, which is created by the other party, they have to take their money. Let's look how we implement this. Yeah? So the idea is now, instead of pushing money into the wallet of somebody else, they have to pull the money out of your account. Yeah, and that's the secure ether transfer idiom. So therefore, the idea is we have a separate, isolated function which needs to be actively called by the sender, pull. Yeah, which is the withdraw operation. Yeah, so in order to get money from somebody else, in order to get money from me, you have to call withdraw, and the withdraw operation is then executed independently from the bookkeeping transaction, which does add balance. Yeah? So therefore, here I allow a certain person that she can get money from me. Yeah? So therefore, I would say add balances, that I add to a table of balances of other accounts for the sender the right to get so much money. Yeah, so that's more or less the bookkeeping task. I add a balance that the person can get it. And at a later point in time, the other person then has to pull the data, and then I look whether there's enough for this sender that wants to now pull money from my account. There is enough money available. Yeah, so I look at the amount he or she wants to withdraw. They shouldn't try to withdraw zero. I don't know why. This would be bad. But it also should be more. So the amount they want to withdraw should be less or equal to the amount balance. So to the account balance I have. And then I would also then update the account balances to zero, and I then, in the context of the other person, the money would be transferred to this account. So that's more or less the code. And if you look now at the history, what we assume what will happen is that you have your smart contract. The caller would add a balance. I would do the update balance in one transaction, and at a later point in time, the person would do the withdraw, which would then update again the account balance and would do the transfer to the caller. Yeah. And so that's more or less, again, here a pulling operation, transferring the ether and not a pushing operation. Okay, another problem you have of Ethereum in some programming languages is that you get overflows, yeah, that you have operations with data structures, and some languages like Solidity don't check mathematic operations, yeah. So therefore, in Ethereum, you yourself have to protect your arithmetic operations against overflow and underflow. Not underflow, against overflow. So therefore, an overflow occurs if you have a fixed size integer and the value gets incremented over its maximum value, or an underflow occurs if you have a fixed size integer with this unsigned and you go, or no, it might even be signed, but you go below its minimum value. Then it wraps around and creates a positive value or a negative value. So therefore, what you now have, you have a library of safe arithmetic operations. For example, it's called safe math. You can look up the code on the internet, and it provides now the basic operations you want to have on unsigned integers with bound checks. Yeah? So therefore, you have an add operation which takes an A and a B. It should be an internal function. It's a pure function. It doesn't have any side effects. And it returns more or less the sum of these two values and throws an exception if an overflow occurs. That's more or less the important point, which distinguishes it from a plain addition operation. So therefore, if you now look at the implementation, we will see, okay, these are the two arguments. It's internal, it returns this with a signature. I would do the calculation with my built-in plus operation. I now create a value C. And now I want to make sure whether an overflow occurred, and it would be an overflow if the value C is larger than the original value A. Yeah, so therefore you had an overflow here. And then you would crash here, you would raise an exception, otherwise you return the value C. Okay, in order to use safe math, the typical pattern is to inherit from safe math, which means that the safe math library is the one you compiled. So therefore, in order to use safe math, you inherit safe math map, which makes sure that you can check more or less the source code, that not somebody else tries to cheat and provide you with some safe math library, which you call on the internet, and behind the scenes, it maybe does totally different things than you would expect. And obviously, if you do multiplication and division, it's more complicated to verify whether overflows occur. Obviously, the disadvantage of using safe math takes more time, yeah, more instructions, or in particular, safe multiplication and divisions significantly slower with the additional checks than plain division or multiplication. Okay, so these are these programming idioms, more or less. They are so basic that essentially you always do them in once. Yeah, like if you have a loop in C++, yeah, where you increment, you have in a for each loop, there's a program idiom how you write a for each loop so that it works as you expected. Then we have design patterns where you more or less compose more than one object. It's not one piece of code which you more or less cut and paste in a very repetitive way, but you more or less design it now and you modify more or less the code. And I think you already mentioned the concept of oracles. Now we want to look at two implementations of oracles, which are synchronous and asynchronous oracles. And if time permits, we then would talk also, but I don't think time permits, we talk about randomness, how to create randomness in blockchain contracts, yeah, because unfortunately, everything should be deterministic. So therefore, if you have a deterministic programming language, which has deterministic behavior, it's very hard to get randomness. Yeah? And therefore, the question is, how can you create randomness in a system which is deterministic, which will be covered then. And then we also have a third problem which occurs in smart contracts. As I said, if you deploy a contract, you can never change it again. Yeah? So therefore, the idea is now, if you want to have evolution support, that you, for example, deploy a large program which has hundreds of functions, the expectation that this huge program maybe has some bugs, you want to do some upgrade of the functionality of this program, would mean that you want to have somehow an evolution support, yeah? That people can call your program, but you have still the flexibility to change the implementation of your program. And that is called evolution support, which is a design pattern. And there are two ways of doing this. One is a data segregation pattern, and the other one is a proxy pattern. And I think next week then we will cover token standards, which are more or less standardized, not only design patterns, but they are standardized ways how to, like standard libraries in other programming languages. And since they are not about file I/O or mathematical libraries or cryptographic libraries, the standards here are typically token standards, how you represent tokens in a standardized way, an interoperable way. Okay, I think we already talked about this. Design patterns are template solutions for recurring design problems. So they are not, in this sense, repetitive, that they are cut and paste, but they are templates, and you have to modify the templates to meet your needs. So now look at the Oracle pattern. What was the driving problem or the motivation? Smart contracts can't access any data from outside the blockchain on their own. So therefore, the blood donation cannot access the clinic or data of the clinic system. It cannot say, I want to be in a clinic which is currently open, if this information is not on the blockchain. So therefore now we need, so it cannot call, let's say, make an HTTP request or a file read operation or any other internal input operation. So therefore, what's now the participants? We have a smart contract which now needs data from external sources, and we also have an external party which is willing to provide data from external sources by a smart contract to the system. Okay, and I think we talked a little bit about the abstract idea, and now we can look at the Solidity code. The abstract idea is, and we talk first about the Synchronous Oracle. So the idea of the Synchronous Oracle is that I have an externally owned account. I call my smart contract, and the smart contract now needs the data. It now talks to an Oracle contract. It calls now does a function call to request the data, and it waits for the returning data as a blocking operation in the sense that it is a function call. So it does a function call to request the data, let's say get current temperature or get current stock price or get current opening hours of clinic, and somehow the clinic is out there of the blockchain, so therefore we have a contract which magically should provide this information, and I want to get the data in a synchronous fashion back, so that whenever I ask for it, I immediately get the result back on-chain. Okay, so in order to achieve this, we now need a separate off-chain Oracle service, and this Oracle service is something like a daemon. It's more or less, it runs continuously every 5 minutes, 5 seconds, 5 days, you name it, based on the probability how often this external information changes. If it's the current temperature, maybe you would say, okay, there's a fixed interval in where we calculate the new temperature. And in this fixed interval, it would request the data from the external web API, like you would do it in a web interface with a service. You get some information back. This may take a long time, but it doesn't matter. After some time, you get back the data. And once the data is received by the Oracle service, in step 3, the Oracle service, whenever new data arrives, writes this data to the Oracle contract. So this means that with a certain freshness, this data is valid. So it's the last data the Oracle has seen is accessible immediately on-chain to Synchronous Oracle. And also you could have, let's say, situations like you have it often on the web, that the external web API would say, this is the current temperature. And by the way, the weather forecast says that the temperature would stay stable for the next the next weather report will be in 1 day. So therefore, the returning data can have some expiration date, and based on the expiration date, now the Oracle service can more or less decide when to do the next request, so that the polling is more effective. There's typical patterns in REST-based APIs that you get some expiration data back, and this loop can be adapted to the speed of velocity of change of the external web API. Okay, so what are the benefits? Oh, now first, how do we do it? So if you now look at the code, you now have a simple Oracle contract, which is exactly this simple Oracle contract, which now has internal, so the simple Oracle should now return the current market prices of Ethereum and Bitcoin. Yeah, so therefore the idea is, so we have now an operation which is called get price, which now returns for a given coin, and the coin could be either the Ethereum coin or the Bitcoin coin. Yeah, it's more or less an enumeration value, and based on this enumeration value, we return the price of this coin, the current market price of this coin. This is a view operation because it is read-only, and it returns in my prices table at the index for this coin. We have, in our case, we have 2 coins. It's an array of 2 values. We would return the current price of that coin. And you could imagine it's not only 2 prices, you could also have hundreds of stock markets, and the stock market prices for different stock market ticker symbols would be stored in this prices table. Yeah? So that's more or less this get price operation. And it assumes, and it has to be publicly accessible, so that now it's an Oracle because other contracts want to use it. So therefore, I have to declare it as being public. Okay, so that's more or less now not protected because everybody should be allowed to do this. Yeah? So there's no restriction on who can call this. So therefore, anybody can use this Oracle. One could also imagine now to expand this pattern to say, yeah, but they have to give me money to do this, or they have to do some, after they received it, they have to do some reputation checking, etc. But this is the plain basic idea to get now this data. So now, this is more or less what we did here. We implemented this function, which is called by arbitrary other contracts, and now we look at this interface where we want to write the data. And that has to be protected because not everybody should update this data, but only the Oracle service, which is the creator of the Oracle contract. So therefore, we now use essentially the same idea we have done before, that we have a constructor, and the constructor more or less defines now who is the controller or the owner of this Oracle, and the controller is the message sender. Yeah, that's more or less. Therefore, we store the controller as an address, and whenever we want to later on update the data, we first check whether the isController is true. And isController obviously is that the comparison of the current message sender of whether the current message sender is the controller. Okay, so therefore the update now works as follows. We first check that the coin is either the predefined coins value for Ethereum or the predefined coins value for Bitcoin, because only for these 2 coins we want to keep track. And if this is not the case, we roll back the transaction. Otherwise, for one of these 2 coins, we update the current price. Yeah, so therefore, this is the update operation. Okay, another option would be to say, okay, maybe if this question only comes very rarely and this data changes frequently, it's a total waste of energy here because it's not only that we consume compute power here, but we have to pay money for updating the Oracle contracts. Yeah, so from the perspective of the Oracle owner, maybe this is a lot of waste of expensive Ether and expensive Bitcoin money to keep this contract alive and up to date, even if nobody asks for it. So therefore, the idea is now, why not to switch to synchronous from Synchronous Oracle to an asynchronous Oracle. Yeah, so the idea is now that we do, again, not if we have a request, the sending contract says, okay, I'm now interested in the result, but I have time. So instead of more or less waiting for the result and blocking, I say, okay, this may take a little bit of a while. And once you get the new data, please inform me with the callback data. That's an asynchronous oracle. It's similar to an observer you have in a traditional programming language. So this contract wants to be notified if Oracle data, new Oracle data becomes available. So therefore, again, it's not the owner of the contract pushing the information, but you pulling it and getting notified once the result is available. So therefore, the Oracle contract now emits an event, and the event more or less now holds the information from the Oracle service, and this event that can be consumed by the smart contract in reading the data that has been provided. So therefore we now have the flow of control would be from the side of the consumer. I call a smart contract, or somebody calls my smart contract. I need, let's say, now the current prices. Therefore, I ask the Oracle contract to provide the prices, and only when once the price becomes available, I expect that the Oracle contract will emit an event, and then I also provide an event handler here, which now takes this event and consumes the event. On the other side, the Oracle service now waits for the event of so that an event is necessary, and once an event has been called, so that somebody now needs data. Oh, sorry, I totally misinterpreted the other way. So I signal. So the Oracle contract doesn't emit an event once new data arrives, but the event is raised that somebody wants to get information here. So therefore, the event is indicating that data is being requested. That's part of this red communication line. Once data is requested, the Oracle service waits now as an observer to this event. And once this event is raised, it requests the data, returns the data, and writes the data back to the Oracle contract. And the Oracle contract itself then sends back the data to the smart contract. Okay, let's look at the code. Then maybe it's easier to follow for some of you than if I explain it. So we now look again at the client here. So we first look at the client code. And the client would say, so that's the client code. And on the other side, we have the Oracle code. And what does the client do? So the client more or less first defines, so the client now essentially wants to do two things. It wants to more or less, first, once it's created, it connects to the Oracle. So therefore, if I now create the client, I now bind it to the Oracle the client should use. I get it as an argument in our case. So therefore, the Oracle is handed in as a parameter to the constructor. The constructor remembers the Oracle. And if now, during the execution of my client code, which may be triggered here, the client now finds out that the client needs the Oracle data, the function getOracleData would be called. And this is a public function, and this public function now takes this Oracle contract, which has been stored here as an address. Maybe it could better be stored as an Oracle object, but now then we don't need to have this downcasting. But since we stored it as an address, we have to downcast it. Sorry, I have to downcast it to an Oracle. Then I store it as the Oracle contract, and then I invoke the Oracle. That's more or less once I need to get the Oracle data. Once I get the Oracle, then I call this function invoke Oracle. And then I have a second function, which is called Oracle callback. And the Oracle callback is exactly the function the Oracle should call when it receives the data. So therefore, the callback gets a data point, which is A, and this data point is more or less the value I was asking for, which is now stored here. And this Oracle callback obviously has to be external because it should be externally called. but it should only be called by the oracle. So therefore, we also have this modifier only oracle, which makes sure that the callback is not called by some malicious party which wants to more or less trick my contract. Yeah, and so therefore, now I make sure that the callbacks only are accepted from the oracle contract. Yeah, and so therefore there's now this asynchronicity involved, that now whatever I want to do with this value a has to be done later on in this piece of block code after the oracle callback. Yeah, so if I want to, let's say, calculate with a, I have to write the code that calculates with a here, and that is very similar what you know from callback-based programming in web application engineering. And then you can do all these things that you have functions here that you define that after the oracle callback, a should not only be stored in a global variable, but a should be passed on to other functions which then perform necessary other operations on the client side. Okay, so therefore, from the perspective of the client, this is an asynchronous behavior, and you have to use asynchronous programming patterns to implement the client and to handle the delay of the call. The oracle itself now looks as follows, that an oracle, more or less once it's created, has an owner, which is more or less the contract. In this case, the owner would be here the external web API, which created the oracle. So the owner is defined. Then we have again the only owner, that only the owner can call it. And then we would have the invoke oracle function, which says, okay, now there is a client which wants to get now some data, and then now the oracle contract should now emit an event. Emit is a keyword in Solidity, which allows to create. It's not persistent events, but it's event objects which are passed in the network. Yeah, so therefore. A contract, so if you create a contract, you can also listen for events as a client. If you are a client, let's say you're the laboratory or you are the programmer of the Oracle service, you not only can issue transactions on the blockchain, but you can also listen for events on the blockchain. And events on the blockchain are generally created with this emit command, and the emit command now creates an event, and this event now consists of this argument defined here. And the event we want to create is, it has a certain, how would you call it, a certain name, the event. It's an Oracle invoked event, and it has an argument, and the argument is the message sender. Yeah, it's more or less the person or the contract that wishes to be informed once the oracle has been invoked. Yeah, so therefore this event is now emitted, and once this event has been emitted, the external oracle server would do its job and calculate the new event, and then invokes the callback operation, and the callback operation now gets back or expects to get back not only the value which has been calculated, yeah, let's say the Bitcoin price or the current temperature, but it also gets back the client that should be notified. Yeah, so therefore the message sender is the client. Yeah, so the message sender is the client, and the external Oracle server now has to pass in again this client ID as a second argument to the callback function. And the callback function then checks that it's only the owner calling itself, yeah, which would be right. Then it computes, extracts the client contract as this client ID, and then invokes the client contract Oracle callback on A, which is then called here. Yeah, and then we get this value back. And as you can see now, this is now this event handling, which now works between these contracts on the chain, but also we have event handling between contracts on the chain and external transactions or external parties which invoke, which interact with the blockchain. I think we are now, time is over. As you can see, it took longer than expected. But we should maybe take questions if there are questions. So the question, I think, as far as I understood it, is so what's the trust relationship between the Oracle contract and the Oracle service? I think if you look at the code from on-chain, which I showed you, it should be clear that the assumption is that once you create the Oracle contract, you become the owner. So therefore, the Oracle contract can be sure that only the owner invokes transactions on itself. So what could happen, maybe the owner was stupid and made his address and wallet accessible and the wallet keys, so that now somebody else, not the Oracle service itself, but somebody else somehow has got access to the wallet and the private keys and could sign messages to the Oracle contract. But I think this is not what you feel would be dangerous. Yeah, I think there we trust that if we get a message from a signed message from a party, it's the party. Yeah, because it's like if somebody has your passport, they can do whatever you like in your name, essentially. So therefore, your question might be, how do I know that the party that now reacts on my event is the Oracle service? But again, it's the same thing, yeah, here, because once the callback is invoked, I have the modifier only owner, and only the owner can sign this callback message. Yeah? So therefore, there's no way for somebody else to create a callback message who is not the owner. Okay, does this answer the question? Okay. Okay. Okay, so now the question seems to be even more further. Why should I assume that this oracle not creates random numbers? Yeah, there's an oracle, I find an oracle, somebody says this is a new super oracle, call us, we give you the telephone numbers of Donald Trump. Yeah, so that's the question. Yeah, so how do I trust that I really get the telephone number of Donald Trump, or that I get the current stock price, or not a random number or an outdated stock price? And there's no chance for you to verify this. This is like with any other app you install in your computer. You don't have access to this source code here. You cannot trust this thing which is happening here. Yeah. So therefore, whenever you use Oracle, you would essentially only can say this person cheated. Yeah? So you would say that obviously the cheating was done by this Oracle service and by this Oracle contract. So therefore, typical patterns you could achieve here is that you say there's a second data structure where you have a community which more or less votes about the credibility of this contract. That they will say, okay, in the past, this would be some community of users of this contract, which now initially test this oracle and validate that these responses are correct and timely. And then they would vote on the results of this oracle and say, yeah, this was correct, and this was correct. And based on this on-chain voting, you could establish trust of the user community with this oracle contract, which would not keep the contract from lying in the future. Yeah. So therefore, then it would go down again. But that's, I think, what we learned more or less in game theory. Once you play these games over and over again, it's in the best interest of the oracle contract not to lie, because only then you can earn money with this contract. Yeah. And that's the same reason why people build a trust profile on eBay, because based on their past transactions that they more or less delivered what they promised, you now create rankings here. Yeah, but it's not really trust because you don't see the source code here, and there could be arbitrary programming errors or spying stuff, etc. Okay? Okay, so we now, I think, spent our time. Again, if there are questions, we can also post them or ask them in the exercise. And otherwise, we will continue next week with the other Oracle, the other programming pattern in Ethereum, and finish the Ethereum chapter, and then move on to other blockchains.
Hi, welcome back to our lecture, Blockchain-Based Systems Engineering. Uli and I are again here. I have a new microphone. I do hope you hear the quality improvement. I do my best. It's a very cool device I got today, and I will become a YouTube star, I think, in the next generation. I think the most important point you might be interested in is not the lecture today, but the exam. Finally, we got the time and the date for the exam. The exam is in physical form, which is dangerous, but there will be a lot of measures to keep you safe and keep the distancing, all the regulations that will keep the whole chair busy, more or less cleaning the room and doing the right stuff so that you can do your exam. There are some of you which are not in Germany right now, which cannot physically participate. For them, we have now a list. Please enter your name as quickly as possible so that we collect your names. And for those people, we will do a parallel version of the exam remotely. Also with several participants of our chair watching that you don't cheat. The details will be announced in written form, but please let us know. And then we also need to prove that you are really abroad, and so that's important. So that's, I think, what is the plan for the lecture exam. Okay, and again, Uli more or less has all the details and sent around already the list where you can enter your name.
Yeah, I'm going to post an update on Moodle during the day and let you know about the details.
Okay, so we want to continue today with blockchain-based software engineering. So we finished last week with Solidity design patterns. We talked about oracles, synchronous and asynchronous ones. Today I want to continue with, let's say, one problem we have with very deterministic execution of the blockchain. Namely, if it's very deterministic, how do you create randomness? For example, if you want to do online games where more or less the outcome should not be known by looking at the code. And that's, I think, generally for computers, randomness is a difficult thing, but even more so if you are in a deterministic system like the blockchain. So therefore, we talk first about this. How do you solve this issue to create randomness in contracts? And the second point is evolution support. If you have persistent data structures and you evolve your software, then you very often have to do schema changes, that you migrate the data from, let's say, one schema, you add a new column, or you add integrity constraints to the database, or you change the cardinality constraints of relationships between objects. And similar things happen over time in contracts, that you initially designed a contract, and then you have to evolve it. It's much more difficult to do this, and so therefore typically the approach is to minimize the amount of information and the amount of logic you put on chain, and then rely on other things happening out of off chain, where you have most of the changes, user interface changes, additional information you attach to contracts. So therefore, we will talk about how you do evolution on the chain and what are the limitations of these approaches. Then we are finally ready to talk about token standards. As you know, the token economy was one topic we mentioned very early on in the lecture, that this is more or less what's the finance instruments of the blockchain are all about. So that you have physical things like or rights or ownership relationships, and you want to tokenize them. And we want to tell you what are these tokens, what are ERC20 tokens, what are ERC 721 tokens, and what for purposes are they good for, and how you can implement them. Okay, so I have to scroll forward to the Oracle pattern. So we had these two Oracle patterns, the Synchronous Oracle pattern and the Asynchronous Oracle pattern. And we stopped essentially here when I explained the Asynchronous Oracle pattern here. that you more or less have an oracle, and the oracle, whenever an event occurs, notifies the client. So therefore, it has a callback function for the inversion of control, that it more or less now sends information via a callback function to a calling client, and then the client executes the necessary operations to receive the result from the oracle. There is a potential problem with this approach, which we didn't mention last week, because this oracle is executing its code with gas from the oracle owner. And if it now transfers this control to this contract here, there might be a risk that this is an adversarial client, which says, yeah, we wait for the callback from the oracle, and here I compute, let's say, Fibonacci numbers, or I spend a lot of gas. Yeah. So the idea is that the idea to cheat here could be that the callback itself executes now a code and does, let's say, allocate data structures and does things which cost gas, but it costs the gas of the oracle. Yeah. And to avoid this, this general problem that if you do callbacks and you call code you didn't write yourself, we show how this is done. This is the limiting the gas usage. And the idea is that you pass as a parameter for the callback function call a gas value, which you permit the other function to execute. Yeah, and that's, I think, again, a thing you have to think about if you have public blockchains, that the other people which more or less integrate your contracts into their contracts might be adversarial. So they have not your idea, which is different if you have a consortium of people which jointly want to do something. They wouldn't try to break other consortium members' contracts if it's a faithful association. Yeah. So here the idea is that you now pass in this gas value, you limit more or less for the other party, and that's done as an additional argument with the syntax in Solidity. Okay. And then you obviously have the problem to say how much gas do you give the other party, and that more or less requires some estimates, yeah. Because if you give it too much gas, they might use it for their own purposes, or unlimited gas. They could consume all your gas, which you gave to your contract, and so therefore you have to do some calculation and inform the users of the callback that maybe they are only allowed to take the value, store it somewhere else, and then have to do other things again with their own business logic and their own contract. Yeah, so therefore this calculation has to be done with a rule of thumb. How much do you want to allow the other party to do as a reaction to your event notification? Okay, so to summarize, we have now seen these two oracle patterns, which allow us to, let's say, make this very autistic blockchain system, which is always self-referential. If you have correct blockchain transactions, they can build on other correct blockchain transactions, but they cannot depend on the reality, on other input. You resolve this by saying, if I need input from the world, I have to have parties which provide me the input, which makes me dependent on these other parties. Yeah, so I now become dependent on third parties because they could cheat and say maybe they give me the wrong data, or they could more or less be unavailable or never call me back. So that would be also a problem for me, yeah, because I not only depend on the data which comes, but also that it comes at a certain point in time. But again, you want to know something about if you have, let's say, supply chain, blockchain contracts, they always depend on state changes of the supply chain goods, for example. Okay, we can now move on to the randomness pattern. Again, the problem is that Solidity doesn't provide any random function generator. Yeah, let's say in the early days, also with BASIC, one very important point was to have a random number generator for games. Yeah, so that the game, if you play it over and over again, it doesn't can more or less does exactly the same thing. So Solidity doesn't provide any binary code to create a random number, because that would violate the principle of determinism, which you want to have for the validation of the contracts. Yeah. So on the other hand, you want to now have, for example, games where you want to have random numbers, yes, because you want to make it unpredictable for the parties what will happen. So therefore, the idea is now that we now have to solve the problem how to create smart contracts which rely on random numbers for computation. So one option would be to have an oracle, which more or less generates a random number. For example, you could have something Wolfram Alpha. They provide a random number generator, which is more or less based on a very complicated physical process where they more or less have a table and provide you random numbers from these tables to make sure that they are provable random. On the other hand, if you now know these tables and you know what the next random number will be, you can do these games which people did in the past. If you go to this, in Germany, we have these gaming machines in Gaststätten, if you go to the bar, where you can push buttons and you feel that your button presses have some influence what's happening, but on the other hand, there are some tables in the background of the chip which determine what will be the next outcome, so that the certification agency can make sure that the machine vendor doesn't cheat, and never has a winning combination. So therefore, there were some cheats that people knew this list, and they knew, let's say, they let play other people until a certain combination arises, and then they say the next game will be mine, and then they started to play. So therefore, these table lookup oracles are not a good solution for the problem. Also, if you have oracles which can more or less participate in your games, it's also a bad idea to give them more or less the right to give you random numbers. But that would be also a potential solution to use an oracle for it. There's another way, which is more or less more linked to the cryptographic things we have on the blockchain. And this pattern is called solution that you use a block hash. If you remember, I had this picture. Maybe I can, you can think about it. We had this idea that you have the Ethereum virtual machine in the middle, and then you have some input parameters in the code, which are more or less the deterministic input for the EVM. And additionally, you have the whole blockchain, more or less, which has been computed in the past, which is visible and which can be taken as an input to your calculation. And in this blockchain, there's one value which is interesting, which is the block hash value. If you look in the block hash value, this heavily depends on the combination of transactions which you had in the past. So therefore, the block hash value is very hard to predict what is the block hash value of a certain block. In particular, of the last block, which has recently been mined. So that's the idea, that a simple contract to generate a random number which should return an unsigned integer value could take essentially the block hash of the current block minus 1. Because the block hash of the current block is unknown. It will be calculated once my transaction has been mined, but the block hash of the previous block can be computed. It's already existing. It's more or less the one, the block on which my transaction block will build. So therefore, the idea would be to take now the block hash value of the previous block and return it as an unsigned integer value. Which would be a very unpredictable number for me to say what will be this value. What's this value? There is a certain risk, but it's very low. I discussed it with Uli before this lecture. So what could happen? So if you are now so who are the people who could cheat? So as a programmer, it's impossible for you to know this block hash. So you can compute the block hash number once it's there, but you cannot change it. You cannot write code to change the block hash, because the block hash depends more or less on the mining pattern, which miners took which transactions and created which block hash number. So therefore, the people which know the block hash are these people which are miners, and they could look more or less at this calculation. As they do this calculation, they could run this piece of code, and then they could find out whether this random number that is created here would be favorable for them if they play in a game which depends on this random number. So if they have the source code access to this whole program, they could decide whether this number is favorable or not. Yeah, for example, if you take this very large number and you turn it into, let's say you look whether it's even or not even or odd. You want to simulate a toss of a coin. They could more or less calculate whether this toss of the coin would be favorable for them or not. Yeah, so therefore the miner could calculate this, and if it's not favorable, he could simply delay the transaction, and so that this is not mined, and that it doesn't lead to the desired result. Yeah, so that's the only option what the miner has. He has to more or less throw away his mining reward, which he would get if he faithfully would mine this transaction. But he would say, no, let's say the mining reward is in the order of several $100. I don't want to get this several $100 to do the mining of this transaction, but I suppress more or less this transaction. I cannot suppress it because other miners could solve the puzzle, and then I'm out of luck. But more or less, I give away this mining reward so that others, so that this transaction, this mining random number is not taken, and that maybe another version is becomes the truth, which is more favorable to me. Yeah, so therefore it's a very limited, I think, chance. But on the other hand, if you play games which are about millions of euro, maybe a lot of miners would say they want to bet on their number, and maybe now the miners would start to say, okay, if I get millions of euros, a lot of miners might change their mining process based on this calculation process. Yeah, so therefore, it's that could then lead to a very complicated occlusion of the miners to more or less delay mining of these particular transactions. Okay, so therefore, so again, I would say I would see it not as a big risk if these are random numbers in some scientific calculation. Yeah, but if it's something where you pay out money to people which can freely apply to your game, this might be a risk. What are other ways to create randomness, which are maybe a little bit also more traceable? Yeah, because you always, if you play online casinos, it would be nice if you could really see what's going on. And gambling, as usual, is an interesting thing people like to do because it's illegal in Germany in certain areas. So therefore, it's also a nice blockchain use case. We also presented this solution to the Deutsche Bavarian Lottogesellschaft, because we're also contemplating to use maybe blockchain-based solutions to more or less give more insight into the process, how they generate random numbers. So here, what's the idea now? The idea is now that you use this commit and reveal scheme. Yeah, if you remember this, this was at the very beginning of our lecture when you spoke about that you can use hash functions as follows, so that you more or less have your own secret. You select a secret, then you take a random value, a random number, and you can now hide the random number with your secret. Yeah, you compute a hash value, which consists of the combination of your own secret and the random number you want to now propose later on. Let's go the other way around. So we have now several parties, one or two or hundreds of parties, which are now allowed to propose the next random number. Yeah, so each party would say, I propose random number A, I propose random number B, and so on. And since they don't want to show their random number, they hide the random number with their secret by computing this hash value of the combination of the secret with the random number. But then they commit this value, which doesn't allow the smart contract to guess the random number, because they simply know this was the committed value of party A. This is the committed value of party B, and these committed values contain knowledge about the random number. Yeah, so therefore, in the initial phase, now everybody can contribute to this randomness and propose the next random number. Yeah, for example, if you play roulette. They could say, now, I want to have number 1, he says number 36, and somebody says 0. Yeah, and they would commit to it, and the smart contract now gets these cryptic numbers and wouldn't know and would arbitrarily choose one of these random numbers, or combines the values of all these random numbers, for example, combining the sum and to divide it by 2. So that would be now create a new random number based on all these inputs. Yeah. And the nice part is now that the parties now can control whether the computation did the right thing, because they see now the contract. The contract should compute this value, and now all the parties would reveal their initial secret, yeah, which allows them to verify that their random number really went into this computation, yeah. And this makes it now possible for all participating parties to see that the smart contract, that even if the other parties, let's say you have 500 other players which try to cheat by more or less always voting on the same number, but you have now control of over your part of the randomness. So therefore, you still have control, full control about the computation result. Yeah. So therefore, I think this is a nice way which gives more or less this idea that more or less you gave the random numbers. Yeah. If you have a magician who plays card games, it's always nice if you give the magician the number he should find out. Yeah, and that's essentially what you're doing here. You give the randomness, or you are the source of randomness, and therefore you can validate that your influence really goes into the final result. So that's a really nice idea. There is still a little problem. Okay, you need now parties to provide this randomness. Yeah? So if nobody does it, the lottery cannot begin. Yeah, so that's more or less this user interaction. But obviously, you would use now a game theoretic approach and say, yeah, but if nobody provides randomness, these parties which don't provide randomness are not allowed as players in the game. Yeah, so they have an incentive also to provide a random number because they want to play the game. Yeah, so therefore you combine now so that you more or less incentivize people to participate, provide the randomness in time. Okay, so far so good. So we are now ready. Or are there any questions maybe before I move on? Not really. Okay. Maybe hundreds of questions regarding exam, no question regarding the content. Okay. So the final pattern we look at is the other problem we have. It's the immutability of the contracts. How do you handle this? And in a contract, you might have two things you want to change. One is that you want to change the data structures your contract is using. Yeah, you want to move to more efficient data structures, so therefore you want to more or less modify the data representation which is encapsulated by your contract. Yeah, so that you find now a better way of doing it. Yeah, so you want to have the same interfaces, the same logic, but you want to have a different data representation for doing it, which is maybe more efficient, that consumes less gas, etc. Or you want to add additional information which is used by other contracts. So that would be one way that your business logic doesn't change, but there are some add-ons to the data structures. And that's the first thing we want to do, and which is done with the data segregation pattern. The second way what you want to do is you want to change the business logic of a contract. This might sound a little bit, weird, yeah, because the benefit of Solidity is that you have immutable contracts. You can rely on that the other party doesn't change the contract. Yeah. So therefore, this idea of changing a contract really requires something, a situation which sometimes occurs, that the other party by accident did something wrong. Yeah, and you know all these examples where people found out that a contract was written in a way which more or less keeps money locked on some account, etc. Yeah, so therefore you also have other situations that you want to upgrade your contract, make it smarter and having more intelligent business logic or better exception handling, etc. Yeah, and that would be typical evolutions you do, that you could get new versions of Microsoft Word, and you're very happy that you get new versions of it. And in order to do this, we need again a way to more or less allow contracts to change their code, and that's the proxy pattern. Okay, so therefore, we now first talk about the data segregation. So the idea is that each smart contract has its own state. And typically, you do this, that you have an abstract data type, in the sense that the state is not accessible is only accessible through the methods of your contract. Like if you have a stack, you only have a push and a pop and an empty operation, but whether the stack is a list or the stack is an array, you don't care, and there's no way of you to get access to the array or to get access to the linked list which implements the stack. But if you wanted to move now a stack from which you want to keep the stack, but you want to say, I want to switch now from an array representation to a linked list representation or vice versa, then you wanted to segregate more or less this data from your business logic. And that's the idea of the data segregation pattern. Let's look at it. So the idea would be as follows. We have a contract, and instead of, let's say, and the contract is represented by a UML object. So therefore, it has more or less local storage here, and it has a list of methods which defined in this compartment. And we now focus on the data storage part, because normally you would have variables like here, like an array here, and an array pointer for the stack, or a linked list, a head of a linked list, and maybe a link to the tail of a linked list, or a counter of the depth of a linked list. So these would be typical state variables which would be stored in this contract. And if you now want to change the data representation, you cannot do this because this data is stored with a contract which is immutable. So therefore, the client now has a link to your contract, and you cannot simply replace yourself by another contract. So therefore, you need to now write contracts in a way which allow you to change your data representation. And this is achieved because you now replace access to your local variables to access to a data storage object. And this data storage object is separate, has a separate life cycle from your contract. So therefore, once your contract is created, you start with an initial data storage implementation. And at a later stage, at this operation, this provides then getter and setter methods, an interface, a data storage interface, which you rely on, like getter and setter methods. And based on these getter and setter methods, you implement your business logic. And if your business logic is unchanged, push and pop and empty is unchanged, but your representation is changing, you could later on have additional methods, which maybe cannot be called by the client, but you as the owner, where you replace more or less the data storage by another data storage representation. You have to fix bugs here in the data, to add additional fields, to change the data representation, while keeping the interface, the getter and setter methods the same. And that's the basic idea, that you now provide this data storage contract, which has public view methods for getting values and public methods for setting values. In this case, in an untyped integer store with keys. We have more or less a store which has a mapping from key values to integer values. As a specific way of storing information, not as a linked list or as a stack, but in this case as an array of integers. And if you have a very low-level data structure, like a mapping from keys to byte strings of integers, then more or less you can store any data in this data structure, and you can more or less change the representation here. Okay. And so therefore, now the storage contract provides more or less the interface for this data storage, and then you have multiple data storage implementations, but your contract instances can remain immutable, can stay immutable, and they refer then to different data storage implementations. Okay, the advantage is more or less that the contract and the client, more or less, the client is not aware of these changes, but obviously you have always this indirection here, and the ability to really change the data storage is very limited by the interface you're having here. So therefore the flexibility is not arbitrary flexibility, but it's very limited because the next data storage implementation has to also implement this interface. So therefore, you have more or less the separation of concerns. The functional aspect is separated from the data storage aspect, and you don't have this abstract data type coupling, what you want to have. Obviously, I think if you get such a contract where more or less the owner of the contract can at arbitrary times replace the implementation of the storage, this is potentially a big, how would you call it, trust problem, because you don't have a control as the client of this contract when this will happen. It also now requires a lot of more or less overhead, because now you have this low-level data structure of integers, and if you want to store here more complicated data structures, you have to somehow serialize them and store them in this data structure, data storage data structure. So I think it needs rather contrived situations where you have complicated networks of contracts which mutually trust each other, which allow some of these contracts to change, to use this data storage pattern to allow evolution at this part of the system. And again, if you do these updates, applications need to be notified about the contract address of the new version so that they then can migrate to the new version of this new contract. Okay. So another version is that you use the proxy pattern. I think proxies, you know the word proxy. It's typically if you have a distributed system and you have some business logic on a remote server, that you have a proxy, let's say, function, which more or less is local to your own code, and then you call this proxy function, and this proxy function doesn't execute the real function, but it simply forwards the request to another remote function. So therefore, the same idea happens now with the proxy smart contract. So the idea is that you want to replace a smart contract with a new version that has a newly deployed contract and has a different account address as the older one. You want to avoid that now all participating parties have now to migrate to the older version, but you now want to notify all these other contracts, which now refer to the new version. So therefore, the idea is now that you have these participants, you have an entity that wants to replace the smart contracts with a more recent version, and a smart contract that implements this, some business logic. Let's go through this. And when would we use it? It would be typically used if you have a vulnerability which is found in one of these smart contracts. As I said, the semantics should be the same, but there was now a vulnerability. Let's say an access control was not correctly implemented, or the gas was wrongly calculated, and you want to change more or less the implementation to fix this vulnerability. So therefore, the idea is now as follows. That you now, the client shouldn't depend now on an implementation, let's say on a concrete real subject, but it should depend on an interface. So therefore, in our case, we have one single action here, which is called do action, and the client wants to perform this do action operation. So that's more or less the contract that should, so that's the interface, which should not change over time. And we now have real implementation, or here in this case we call this interface a subject, which now does an action. Here we could have something like a farm, which also has an operation do action, and therefore this would be the interface farm. And now we have a real farm or real subject in this case, which is one possible implementation of this interface. It has a do action implementation, but we don't want the client to directly bind statically to this do action interface, but we only allow the client to bind to this interface. And now we have the opportunity to encapsulate the real subject with a proxy object, which also implements the real. So both the real subject implements the subject contract or subject interface, but also the proxy is a class which implements the do action the subject interface with the do action operation. So therefore, the client gets now access to the proxy, and the proxy, whenever the client calls the do action operation, has a do action operation which does nothing else than take the arguments of the do action, passes on these actions to the delegate, which was created when the proxy has been created. So it forwards now these do action arguments to the do action of the real subject, to which the proxy delegates. Again, the proxy could also delegate to another proxy. You could have a chain of proxies which delegate to each other, but for the purpose of exchanging it suffices to have one proxy. So therefore, the proxy forwards the do action request to the do action request of its delegate. The delegate does the do action. If the delegate is a real subject, it will perform the real action and then computes a result, and the result would be returned to the proxy, and the proxy would return the result of the do action operation. Yeah, and that's more or less exactly what we do here. So that the do something operation we perform here, or the do action operation, more or less takes the real object and performs the do something operation on the real object, and here we don't have a result, so therefore no result is returned. It's only more or less this operation is performed. And this allows us later on to modify the delegate, so that the delegate more or less now can replace this real subject with a real subject 2 or another instance of the same contract. Okay, and that's more or less the basic idea, to use proxy objects to later on replace the real subject here. Okay. And obviously, the update of the logic address would be only allowed by the owner. Not the clients could do this, but only the owner would be allowed to redirect the delegation link to another subject. Okay, I think that should be clear. So, so the benefits of the proxy pattern are that you have, again, the separation of concerns. The clients need to know what they need to know from the contract. The owner has to know how the proxy works. You can also update the business logic straightforward. Also, the clients don't have address change. They still go to the proxy object. And you can now fix also bugs in the contracts. The disadvantages is obviously the trust problem. If the maintainer or the owner of the proxy does not the right things, so he replaces it with malicious business logic, which you don't see, you have to trust that this doesn't happen, and the interface still is immutable. So therefore, the interface, if you need additional operations, they would not be available to the client, because the client only sees this interface and wouldn't see new methods you have here, which have been added by the implementation of the real subject. And obviously, it's like this interaction of the proxies makes it harder to read and verify the logic of a smart contract, because you always have to say what are the possibilities, who can change when the delegation target. Okay. And obviously, you now have, even if you never change anything, you have this interaction that you have an interface, a proxy, and the real thing, which creates additional code and which needs to be deployed. Okay, so that is essentially, let's say, design patterns which are necessary also, and therefore I mentioned them for all blockchain-based systems, because there are specific issues which come from the immutability, from the determinism, and from the also determinism of the underlying execution engine. Now we want to look a little bit more at a higher level. So what are the typical standard libraries you would expect from a blockchain-based language? And contrary to what you would expect from, let's say, your favorite programming language, BASIC or Python, you wouldn't talk about file I/O, socket I/O, and math libraries, but more frequently you would look at token systems, so or web applications where you would have form-based inputs. That's the typical libraries you will find and you learn in your studies. And now for blockchain-based systems, you want to know, how do I implement tokens? And that's more or less the subject. And we do it now on the Ethereum blockchain. So the typical way tokens have been implemented in the past, before Ethereum existed, was that for each new token you create a new blockchain which implements your favorite token, gaming tokens, or tokens which verify the membership of you in a club, or tokens which represent some objects you own. So these were the typical token implementations of blockchains. And since we now have a programmable blockchain with Ethereum, the idea is that we now can implement our own tokens on top of the Ethereum blockchain. So therefore, it's sometimes also called that Ethereum is one system ruling all these other token systems. So therefore, many of the tokens which have been created, or ICOs, are based on Ethereum, because it's much cheaper to use the existing, or much more risk-free to create a token system without asking people to have new miners for your own Bitcoin or shitcoin. You don't have to have a set up mining network. You don't have to have clients, special purpose software for running your token system. It's much easier for you to simply say everybody should use Ethereum contracts, Ethereum wallets to pay. So you also pay with Ethereum, but the tokens are represented on top of Ethereum with these ERC20 standards or ERC 721 standards. So therefore, we first have to understand what two kinds of tokens exist. So tokens are now shown as these tokens, as the English word suggests, like chips, more or less, you can put on the table. And there we have fungible tokens, where all the tokens have the same value and they're indistinguishable from each other. So these are, for example, voting rights you have, and you can accumulate voting rights, 1, 2, 3, 4, 5, 6 voting rights. Or you have money, so you have €1, €2, €3, €4, €5, €6. So therefore it's about quantitative information, and you want to become rich, you want to own a lot, maybe, or this is a piece of land, not a specific piece of land, but let's say 1 acre of land, and you want to have lots of acres of land. Or you have a lottery, and you have a lot of lottery tickets, and all of the lottery tickets, for each token, you can participate once in the lottery. It's more or less like an entrance thing. So these would be typical quantitatively measured things, which work for many use cases. Then there are other tokens where each of the tokens has its own identity. So we have a green token, a yellow token, an orange token, and so on, which have in the end an ID. So they represent one unique thing, which is distinguishable from all of the other things. So that's so-called non-fungible tokens. And you want to have now a management system for these quantitative-like tokens, fungible tokens, and you also want to have other token systems which allow you to more or less work with such collections of wallets which now contain different things. Imagine you have something like a Pokemon game. So people are not interested to have a lot of these green Pokemons, but they want to have different Pokemons, and in the end, they want to collect as many diverse Pokemons as possible. So therefore, these are now these two classes, and obviously, if you describe them as contracts, they have different contracts, because here it's like if you have sets of objects and you have lists of objects, they look similar, but they have now different semantics and you have different operations on them. And so therefore, these are then called ERC20 tokens because they have this protocol, which is the same for all of these fungible tokens. And if you have these non-fungible tokens, there's also a standard, the ERC 721 standard, which allows you to manage that kinds of tokens. So again, the ERC20 standard. So ERC comes from the word Ethereum. What's it called? Reference. So it's more as a proposal. Maybe I don't know the abbreviation. Ethereum request for change. So the idea is, like in Bitcoin, we talked about it. So if you now want to define something like it's gendered in Java, you would make a proposal that there should be a new library called ERC20, let's say the Java token interface, and then you would have a lot of white papers describing what the Java token interface should be, and then more or less this could become part of the next Java certification. And the same thing happens also in Ethereum. You have a request for change that people said, and this request for change was number 20. which says it would be very valuable that not each user invents their own token and has different words for how to do this, but that we have a standardized contract with standardized semantics, which describes now an interface to arbitrary tokens, to so-called ERC20 token interface. And the idea is it's not like push, pop, and empty, or get first, get last, whatever. But it's now this idea that if we talk about tokens, we want to say, for example, what's the total supply of tokens? Yeah. How many tokens are in existence? Then you want to say, what's the balance of a certain person? Yeah, of a token owner. Yeah, if I want to say this is Mary, how many tokens does Mary have? Yeah. Then we want to have an operation which is called transfer. That I now want to transfer. That Mary wants to transfer to Bob 5 tokens. Yeah, so that's more or less here the idea that you say the to address, and you as the owner invoke the transfer operation, and you allow to have this number of tokens be transferred to the receiver. So that would be the transfer operation, and then there's also another transfer operation which is called transfer from, where more or less you want to transfer from a certain address to a certain address and not from your own wallet address, and you define the number of tokens. Yeah, it's rather obvious, the idea of tokens, that you have in a game, yeah, people own tokens. That's the ownership thing, which allows with balance off, you can find out who are the account owners and how much do they own. But there's no identity of the tokens. Yeah, you simply know how many things you have. It's all about integers, and integers with accounts, more or less. What you also have is now, and then you have this active process of transferring tokens, actively transferring tokens from you to others, or from one spender to from one address to another address. You also have the other idea, which is this push. So this was pushing. Yeah, you push tokens from one source to another. Another idea is which is often very strongly related. We talked about this. That is much better sometimes to allow others to take money from you. Yeah. So the one thing is you go to the store desk and you pay with your tokens. That's this active process. But another process is that you permit other people to deduct money from your account. Yeah? So therefore, you simply allow the later transfer of money. And that's the second idea, that now for each address, so a token owner allows a spender the other way around. You can approve now that a spender uses tokens can expand your tokens, more or less. That's the idea, that you approve more or less the later transfer of money to a given spender. Yeah, that's more or less the other way around. It's something, if you say to the tax authorities, I allow the tax authorities to deduce this amount from my account whenever they like in the future. Yeah, so therefore this is more or less the dues, more or less, you have to other people. Yeah. And to find out now what's the allowance of a certain token owner, he can then use the allowance operation as a token for a token owner, and says for this spender address how many tokens are remaining to be spent. Yeah, that's more or less to find out whether the allowance has been given without spending the money. So therefore, this is the other way around, that you have the approve operation, which more or less allows somebody else later on to transfer the money. So that's more or less the active interface, like a REST API for your contracts. And you also have a public variable, which is an interface, so therefore it's constant. You cannot mute it, which is the total supply of coins here. Yeah, so therefore, when you create a new ERC20 token, you have to define the total supply, which is then returned by the total supply here. So that's more or less the REST API, which allows you to do these operations. And this interface more or less doesn't tell you how this is implemented, but the semantics, what I told you, is written now as comments. Yeah. So therefore, if you look at this ERC20 standard, it's like if somebody talks about stacks, they would say what is push, what is pop, what is empty, and what I told you by my words is then also part of this ERC20 document, which says what is a legal implementation of the ERC20 interface. I didn't mention up to now the event, transfer, and approval. And this is, again, something important, which sometimes people forgot when they build token systems. You remember that you have this situation that you want to be notified if somebody else does something. Yeah, so you want to more or less be an observer of the blockchain. Yeah, so therefore, what now in ERC20 interface also requires you as an implementer that you not implement only these REST-based functions or REST-like functions to do this, but you should also create events when a transfer of coins took place. And you should also raise an approval event once somebody approved an amount, once a token owner approved a spender to later spend a certain amount of tokens. Yeah, so therefore the idea is you want to make it observable, more or less, these tokens, so that you have a token layer, and on this token layer people could more or less spend tokens, transfer tokens, and approve the transfer of tokens. But then you can write a higher layer of contracts which monitor more or less what's going on. Yeah, whenever tokens are moved or spent or approved, you want to do certain things. And this is the idea of these event notifications, that either other contracts or wallet owners can monitor what's happening in this network, yeah, and more or less write code depending on the transfer of other people's tokens. Okay? Mm-hmm. Okay, there are questions now?
Yeah, so we got 2 questions. And the first question is, there is the keyword indexed in both events. Did we already cover this? So the event transfer and the event approval has the address and the address from and address to always indexed. Maybe we can say a word about that, what this index keyword means. The idea behind this index keyword is that it allows for easier search and retrieval. So if you have an external application accessing the blockchain, then it's much more easier to search through these lists of events, because you can now filter by these indexed values. So that's just a more easy way to access data. And the second question is, what is the difference between allowance and balance? So I think that's not everyone clear.
Yeah. So the idea, if you would do bookkeeping, or maybe if you look at the implementation later, it's perhaps even clearer. So, but the basic idea is the balance is what you own. Yeah, this is if you go to a bank and say how many tokens, how many money do I have on my account? So how many tokens do I have on my account? Let's say how many euros or how many US dollar. Yeah, so the tokens are you have different tokens. You have US dollars. You have so therefore you maybe go to your bank and say how many euro do I have on my account? That's my balance. And the other thing is if you go to the bank and says, in the past I told you, in the future, let's say for example, today I bought an apartment, yeah, and therefore what I essentially would say, I allow now the other party, I allow the other party to take the money from my account. So therefore, the bank would have a list of other people which I allowed to in the future take money from my account. And that's essentially the allowance. So therefore, for a certain, for me, for example, as a token owner, I can find out for arbitrary other spenders whether they can get in the future money from me. They still are allowed to get money from me. And this is the remaining number of tokens they can claim in the future from me. So initially, nobody has the right, because if I never approved something, this would always return the value 0, because nobody is allowed to get any money from my account. But once I wrote approve to, let's say, my new the seller of my apartment, the seller of the apartment, to take now money from my account, I would allow this, and then he could ask, or somebody else could ask, how much if this is me, my address, and this is his address, he would get the remaining numbers he could still claim from me. Is that clear?
Yeah, I think so. And
Okay.
there's an additional question to that. The total supply is different from the balance, and I'll shortly explain this. So the balance is only of one account, and the total supply is of all accounts.
Yeah, exactly. That's the so the idea is here. So how many tokens are in existence? Yeah, and that's more or less the total supply. And balance off is the individual ownership of one user.
Yeah.
And obviously the idea is, as I always said, you don't want to create tokens out of thin air. So the total supply is there, and you only can shift these tokens around and move them between accounts. Yeah, you cannot, let's say, create. So this is more or less a zero sum game, because the idea is the tokens cannot be copied. Yeah, you cannot create copies, or you cannot destroy tokens. Okay.
Yeah.
Okay, so that's the basic protocol.
Questions.
Are there further questions?
No,
okay.
No further questions.
No further questions. Okay. Okay. And obviously, once I told you this, you would say, "Oh, I know what I implemented." Yeah. So we now look at the implementation, which is called the reference implementation of this interface. But then you would wonder why, if there's a reference implementation, why we do this whole thing of having an interface here? Why not simply have one implementation? And the idea is again that you want to maybe add additional rules to your system, so that you maybe fees may be calculated, or there are limits more or less that certain transfers are not allowed. So that's the idea, that this is the basic scheme. Let's say if a mathematician would say this is something, a ring, or an algebraic structure, and these are the properties of this algebraic structure, but then you could now create additional constraints. So this has already a lot of constraints. The typical constraints of tokens which cannot be duplicated or deleted. That's more or less a token game. But you want to add maybe future roles to this token game. So that certain rights, people get certain rights once they have tokens, or that they are not allowed to have too many tokens, etc. So that's more or less the idea, that the implementation of these functions could later on be more different from the one which I will show you right now. Okay, so this is the so-called reference implementation of the ERC20 contract, which implements the interface ERC20. It uses the safe math library, and we have now these two data structures which are important. And these two data structures, or maybe we start with the easiest one. We have the total supply, which is a private unsigned integer with 256-bit length. So that's more the total supply, which is initialized, obviously, if we create the whole token. But before we talk about this, let's look at the two data structures we have. The one data structure is what is the bookkeeping thing, where for each address in existence, or no, for each, so we have a mapping table from addresses to the balances of these accounts. And it's a private data structure, and by convention it has an underscore as a name to make sure that's a local variable, and a private local variable. That's the table of balances, which maps for a given address to the balance of that particular address. And initially this mapping table is empty, so therefore nobody owns any coins, or the balances are all zero. And the other thing is now a mapping table, which now talks about the allowances. And the idea is, again, it's named allowances with an underscore. It's a private mapping table. And the mapping table now maps each address to a mapping again of another address to an allowance value. So therefore, it's a two-dimensional matrix, more or less. In the rows, more or less, you have the people which allow something, and the columns, you have the people to which they allow to later on deduct money or deduct tokens. Therefore, it's a two-dimensional or two-stage mapping table, which takes the first address, which is the owner, and the second, which is the person to which something was allowed, and then maps to the actual value of remaining tokens that can be deducted. Now, that's the basic data structures here. And then we have the total supply. And we use safe math to not run into problems with overflow and underflow. So that obviously we can now define the implementation of total supply as a public view function. Yeah, it can be called by external contracts. It's a view-only function, so therefore it doesn't create side effects, and therefore it's also cheaper in execution. And this returns now a UE integer value, which is the local value total supply, the private variable. If it want to return the balance of a certain address, it's also a public view operation. It only reads data. It doesn't modify the accounts. It returns the balance, a single value here, and it simply does lookup. It does look up in the balances table at the account position and returns the result. Okay, so and it's also important that this lookup operation has the default behavior that if you look up at an account which doesn't exist or which is out of bounds, it also returns a 0. Yeah, so therefore the balance of, if this mapping value is not in the balance tables, the behavior is not an out of bounds error or whatever, but you get then a 0 as a result back. That's important to know how these mapping tables work in Ethereum or in Solidity. So then we have now the transfer operation. So therefore, I want to transfer money from my address to a certain amount to a recipient address, and it should return Boolean whether it has succeeded or not. So therefore, the idea is now we try to perform a local transfer operation, which is more generic, which is more or less our how we call it, the standard implementation of transfer, which does the necessary transfer operation and also calls the transfer event. And we now call this internal transfer function with me or with the message sender. Sorry, this was not with me, but with the message sender and the recipient, which is given, and the amount which is given. We forward this to the transfer operation, and either this crashes because overflow operations or something else, or we return true to indicate that the transfer was successful. Then we have the allowance operation, and the allowance operation does the following. It looks for an owner and a spender, and it looks up in the allowance table at the position of the owner. It gets a mapping, and then it looks at the spender position to return the UE integer which is stored there, and returns this value, which provides me a read-only access to the allowance. Then we have the approve operation. The approve operation again has additional requirements. For example, that the spender cannot be the 0 address. So therefore, this will be validated. So therefore, we have a spender and the value. And again, the approve operation takes this message sender object as the first argument for the internal approve operation, which then performs a transfer from this address to that address with this amount of tokens. And if this was successful, it returns true. Then we have the core operation, which is the transfer of tokens. Yeah, so that's more or less where the interesting stuff happens. That we now want to perform a transfer from an address to a recipient by a certain amount, and we want to return true if this was successful. So therefore, what we would do now is that we would perform a transfer from the sender to the recipient with the amount, and additionally, and that's one transaction. That's important now. That's one transaction. It either fully works or it doesn't. It completely fails. Yeah. So therefore, we don't have visible states which only have this transfer, but it more or less performs two things. It transfers the sender money from the sender to the recipient this amount, and additionally, it approves from the sender. It also reduces the it reduces now the amount from the allowances. Yeah, so that's the idea, that it allows now the sender to it approves that later on the message sender gets from the sender address this reduced amount. Yeah, so it reduces the allowances by the amount that has been transferred. So then we have the transfer operation, which more or less now does balance updates. So the transfer operation, again, sender recipient amount. It's an internal operation. It cannot be called externally, so therefore it also has this underscore. It now performs the balance updates in an atomic way. Yeah, so that it first requires that the sender is not a nil address and that the recipient is not a nil address. So it's a valid address. And if there's an exception, this is the error message you will find in the log, that this would be the error message that the transfer is not allowed from a 0 address, and the transfer is not allowed to a 0 address. You are not allowed to delete tokens by simply sending it to device 0. So once both are existing valid addresses, we can now do the atomic update, that we subtract the amount from the sender amount, from the sender account. We reduce the sender account by the amount. This could fail because we use safe math, which would then kill the whole transaction. Yeah, if you don't have sufficient funds, this would fail with an error message that there's insufficient funds on the balances account. And then we would have, once this was successful, we would increase the balance of the recipient by this amount. And again, it should not overflow, but I think that is only a very hypothetical problem here, that it could overflow. And once these two operations were successful, we would emit the transfer message, which with the sender, the recipient, and the amount. Yeah, so that's by more or less rerouting all the transactions to the transfer operation. We can make sure that all successful transfers of money will lead to this message or to this event being distributed in the blockchain network, which can then be catched and looked at and searched for by other wallets and other operations. The approve operation also does nothing else than doing a little bit of bookkeeping. Yeah, again, so the core approve operation, the internal one, has now the necessary information. It says owner, it has a spender, and the value that should be approved from the owner to the spender. Again, we do the sanity check that both of them are not nil, and then we assign the value at the position in the allowances matrix at the position of the owner and the spender. We override the existing value with this value. Yeah. So therefore, approve doesn't increment it, but it more or less approves this value. So therefore, with approve, you can both do reduce the approved money, or you increase it, but you more or less define the existing amount. Yeah. And then the approval operation itself, once it was successful, raises this event with the owner, the spender, and the newly approved value. Okay, I think that is the whole implementation. And again, since, how will you call it? It's all about money. It's important more or less to also look at this implementation, what could go wrong, what are the edge cases, and that is also a benefit of this ERC20 reference implementation. It's more or less a boilerplate code you could use now to do more fancy things like calculating the sum or defining limits of coins that may be owned, or updating extra data structures in addition to the accounts. Okay, there are questions?
So we got 3 questions. The first one is, do you get the amount of tokens if you call the balance of another user's address, or is it secured via the isOwner modifier?
Can I ask, so the question, we can go back?
Yeah,
Balance
so
off?
the balance off.
So if you could look, if you look at balance off, so there was no. So currently there's no. How would you call it? Restriction, no modifier. So everybody could call it. So it's therefore looking at the signature, there would be no limitation that you could ask the balance, let's say, of the queen or of your professor. Yeah, so you could now look at the information here. The interesting question is now, if you now have an implementation which does these checks, which more or less modifies the code, this is valid. Yeah? So that's exactly what I said, that this is now that you restrict the rules of the game. Yeah? You have a superclass, or you have an interface which defines general rules of a game. And now you say, yeah, but I want to maybe limit this to only that I can ask the account my own balance. Maybe it's the only thing I'm allowed to know. Or there might be access control rules where I give rights to look at the balances of other people. I create groups of people, so I have different token holders, etc. Now, this is essentially the idea why you could have different flavors of tokens. Yeah.
So I want to add to that question, because I think it's important to get an understanding here. If you would restrict the function balance off to only owner, or to basically to the one who's asking the question to check his own balance, you could do that definitely implementation wise, but you could not prevent this information from leaking. So there is a potential way to look into the memory, into the storage of the Ethereum virtual machine, and get the data regardless if you limited it in the visibility, so to say. So that's the important part here from my perspective. And I wouldn't do that because I would not restrict that, because it's it does not make sense, and you would definitely break a little bit of compatibility with other parties if they could not check the simple balance of an account. So I would not do that.
On the other hand, these are these two different answers. Yeah. So the one answer is, I think, if you go to the lower level of the system, you always could not only get the current balance, even previous balances. Yeah. And this is then, from a legal perspective, also the problem of blockchain-based systems, that you can never delete something. Yeah. Nevertheless, if you if you would more or less limit more or less your business logic. Yeah. So as usual, you would. So there are two levels. Yeah. So if you want to define business logic, it makes perfect sense to say, at the level of the business logic, I don't want this to happen, and therefore I could also express it. Yeah, and to say I don't want this to happen as part of the contracts or as part of the normal execution. But obviously, then, as Uli said, if you go down to the level of the virtual machine, or to go to the blockchain, and since it's a public data structure, everybody can do it. There's a huge risk that people then, if this is very, very important information, that it gets leaked. Yeah, it's simply, here you define protocols between your contracts, where you can enforce certain things. But you always have to be aware that the data structure itself, which is generated, contains all the information, and experienced people could get at this information and make bad use of it. Okay?
Yeah. Okay, continue with the next question. Is it a convention that only all private variables begin with a / with a, for example, the balances start with a underscore, or how would you call that?
Yeah. So the idea is more or less, it's a matter of taste, I think. Yeah. So to my understanding, but I'm not the super duper expert, I don't think that this has any. Maybe some linters would check it. Yeah, that you do it. That's a convention. Yeah. So that if you read the code and you have. Because here is very often you have the same word here, account, and here, that you want to distinguish local state variables from parameters or from function names. Yeah, so therefore that's a convention for private or protected variables to use this.
Yeah, that's true. So it's just syntax. And the last thing I want to say, the last question we have for this section is, why does the underscore transfer method never look at the allowances to check if the transfer is actually allowed? So we have this internal, if you go,
This
I
one?
think, no, if you,
To the implementation?
The implementation of this next slide.
Yeah. The actual transfer.
So why does this not check if, for example, why does it not verify that the balances are correct?
Yeah, the idea is now, if you have an underflow, this would raise an exception here. Yeah, but it's unsigned, and it's an unsigned integer. And if you would go below 0, then you have a wraparound, and you get a positive value. Yeah, so you would get a very high value, and the safe math library sub operation would raise an exception. Yeah, so therefore the subtraction, if it goes into 0 and it's an unsigned integer, this would create an underflow. Yeah, and that would. So therefore, it doesn't need to check it. It simply does it because the check is in the sub operation of the safe math library.
Exactly. Okay, very well. Okay. No further questions from Tweetback. I think we can move on with the next slide deck.
Yeah, but again, I think these questions are nice because you see, this seems to be a very simple contract, but in the end, it already is very factored more or less. So it has two aspects to it. So one is more or less that it caters for several situations. For the very frequent case that I want to transfer my money, that there's a short form for it. Whereas there's also this opportunity to move money between other addresses. Yeah. So therefore it's more or less was a little bit forward-looking. If you think in terms of the old books Bertrand Meyer had about contract-oriented programming, he also talked about this, that the benefit of having good libraries is that they not only solve the current problem, but also future problems. And the future problems are also this idea that it's a very good practice to allow others to observe the behavior of this flow of coins. So therefore, this ERC20 interface is not a minimum interface, but it's a useful interface. What's also nice is here that you see, even if it's a very simple business logic, you now have also the right spirit that you always think about what could go wrong. Yeah, and I think this is really what you really need if you write smart contracts. That you think about the worst case scenario. Who could try to use the wrong addresses, the wrong numbers, whether it's unsigned or signed integer? I think these are very, very crucial things because you have a lot of attackers around because it's all about money. Okay, fine. So if you now created your own token, one nice benefit of using this contract interface is that you get a lot of ecosystem around it. Yeah. So therefore, if you define, for example, the blockchain-based system engineering token BNB, and you would deploy this, then you would have more or less. So you would automatically could have a, because it implements the ERC20 contract, you could now use services which exist on the web, for example, to view the status of a certain ERC20 token. Yeah, let's say on a certain exchange. If you now say, I want to introduce this new token, let's call it BNB. We have this abbreviation here. Then you could automatically say, what's the total supply of BNBs? How many people hold currently? How many non-zero entries do you have in this holder address? And how many transfers happened in the past, which can be seen from the transaction log. Yeah. So therefore, you have now tools based on this convention that is an ERC20 token, which already allow you more or less to talk about and trade with these tokens. Yeah, because the trading of tokens on a stock exchange uses the same protocol. Yeah, and so therefore now other contracts, higher level contracts like market makers or like here statistic analytic functions could now use this knowledge that you implement the ERC20 token to add value to your existing tokens you're developing. Okay, and so there's some statistics. For example, if you look at these exchanges, then you can find out how many dollars are people willing to pay for this tokens, and what's the total market capitalization for the total supply of these tokens, and so therefore if you now add up the market capitalization of all these, some of them are very valuable and others are shit tokens, have zero value, nobody pays for them, then you get a total market capitalization of $12.4 billion. I think that will change over time. I think what's going on. So therefore, don't take this for serious and invest in it. But that's the idea. You could look at the current market capitalization here, and also how many token transactions have taken place, and how many different token contracts exist on the main network. So a lot of people created these tokens. Which obviously only a very limited number of them has a real global value, like let's say some Bitcoin-like token. Okay, so now we can move on to the next standard, these non-fungible tokens. So therefore, the idea is if you now want to have assets, so valuable things, assets, like a house or a crypto kitty token. We want to represent one of these fake or virtual animals, or we want to represent a specific Pokemon figure with a certain power. Then you want to more or less, or you have a unique artwork, a piece of art, or a piece of, or you want to represent your device which you own, or the ownership of your particular device, then you use non-fungible tokens. And you can also talk not only about positive ownership of things, but also negative value assets. For example, I owe you something. I gave somebody some money, and this fact that there is a existing negative value asset alone can also expressed by such an ERC 721 token. So you will find some similarities, because you want to transfer tokens, but it's no longer valid to say you transfer a set of tokens, but you have now a list of tokens, or a bag of tokens which have different identities. So the order of the tokens doesn't matter. There's no hierarchy between the tokens, big house or small house, all houses are created equal. But it's important to know which houses, which set of houses, which collection of houses you own. And it's not just the sum of houses you own. Okay, so therefore, if we have now this token standard here, it requires a certain Solidity compiler of a certain version, at least of that version. And this is more or less the source code you will find with the additional documentation of this token standard. Let's go through it. What we have here, we have the balances of the owners. So the idea, if I look at the balance of an address, I want to get back for a given ERC 721 the balance for that particular owner. Then if I have a given token ID, I want to find out who currently owns this house or this contract, or this loan, which returns then the address of the current owner of this particular token. Then we want to have a safe transfer from a given token, from an address to an address. This is the token ID we want to transfer. And then there is some additional information we can pass along additionally in this contract. So this is more or less, again, an extension point that it turns out if you want to transfer unique tokens, you sometimes want to combine this with another atomic exchange of data. And this data can be passed in as a stream of, as an array of bytes as an additional argument to the safe transfer operation. So then you also want to have, and this is an external payable operation, so therefore you also can combine this with a money exchange, so that the token that you give money, let's say Ethereum, Ether, and you pay with Ether for this transfer. Yeah, so that's the idea. Therefore, it's a payable function. Yeah, that also is allowed to cost money. Then you have a safe transfer from operation with the same arguments without this additional ability to attach data to it. It's an overloaded function. Then you have a safe the transfer from operation, which again has the address, the sender and the receiver, and the token ID, which is more or less from the signature wise the same operation, but we will later on see what the difference for safe is. Then you have so that's more or less the transfer part, the active part, as we discussed it with the fungible tokens. Now we have the same idea that we can approve the later transfer of a certain token, that I can approve another person to do this later transfer. Again, this may be combined with a money transfer of Ethereum. So then what else do I want to have? That I say I want to allow another person, the operator, so I want to allow an operator to access all my tokens which I have, and I can either say I allow this with approved yes, or I revoke the approval by saying this to false. So therefore I can set the approval for all my tokens I own to a certain operator, all at once to true or all of at once to false. I can find out the number of approved things. So therefore I want to find out for a certain token who is approved to get this token. It's not the number of tokens, but who is allowed to get this token, because I allowed somebody else to get it. And who is this person who is permitted to get this token? And obviously there can be only one person that is approved, because it doesn't make sense to approve several people to do it. And then I can say I want to get now find out whether an owner is now, if for a given address, the operator is allowed to get access to all of the tokens. Yeah, and if this is true, if the operator is approved for all of the tokens, I get a Boolean result, a true back. So therefore, these would be more or less the protocol, like my REST API. With the additional information that we also can transfer money for these individual tokens. And then we have these events which allow me to observe the behavior of this network or of this token. We can look at the transfer events, which again, as already indicated, are then addresses from, to, and the token ID. And like in an Oracle database, you can now say these should be indexed. There should be a secondary index, which allows you to quickly look up transfers based on sender, receiver, and the amount. And we have also events which allow us to validate or to be informed about approvals of owners to certain receivers for given tokens. And also this approval for all operations has a separate event which is raised once it is executed, successfully executed. Okay, so the mathematicians would say it's up to the reader to implement this. I also do this now. You can look at the code implementation later on, because it doesn't make sense if I read now every line of code. So therefore we forward you to the implementation on the web. Okay, are there any questions? Mm-hmm.
So there is one question, and the question is, can you again please explain what the balance is in ERC 721? So there's a function balance of ERC in the what exactly does it count?
Yeah, so it doesn't check. So here we have two options. One is I'm interested whether a certain person owns a certain token I'm looking for. Yeah, so I have a token. So sorry, I have a token, and I say who currently owns this my phone. Who has a token for my phone? Yeah, that would be the owner of question. Find me the owner of a token. The other idea would be you have a person, Peter, and you want to say how many things does he own, yeah, and therefore you would now find out the balance, the number of tokens. Yeah? He has, let's say, one phone of me and one phone of Uli, but I don't care which phone he has. I simply want to know the number of individual, let's say, phones or pieces of land or pieces of art. Yeah, so that's more as a count. Yeah? So that's the balance.
Independent of the quality of the token, this is what it's counted. The amount of tokens is counted.
Yeah. But
okay.
For all, yeah, the number. Okay, fine. So
yeah,
no more questions?
One question, could you explain this again, please? All tokens have a combined market cap of $12.4 billion. Ethereum without token has $18 billion. So to update on that, I have just, I did not update this on the slides, unfortunately. Ethereum has 25 billion right now, and all tokens have about 20 billion US dollars of value. And what is the difference between them, or why is it that way?
Okay, so we have now two layers. Yeah, so one layer is the built-in Ethereum token, yeah, so which is more or less part of the platform. Yeah, so you have a platform token with which you run contracts. Yeah, and you can run game contracts, etc. So that's Ethereum chain with Ether, and therefore you can more or less. Yeah, so therefore Ether has a certain value, more or less, market capitalization for running smart contracts. And then some of the smart contracts implement tokens. Yeah, and then people are willing to pay for these tokens. For example, if people play kitties, yeah, where they create kitties and they trade kitties and they bet on kitties, they then invest money not in Ethereum, but they additionally, so they pay Ethereum for playing the games, but additionally they pay money for these kitties. Yeah, and so therefore you now have money in the platform for running the platform, or people hold wallets with Ether. And additionally, you have now wallets implemented as balances in a contract. And if you can trade them, and you can go to an exchange and say, okay, who's willing to pay for these kitties? Or who's willing to pay for my SEBA Bachelor token, yeah, or for my Corona token. Yeah, so that's the idea. So therefore, you have people which are willing to invest money into these assets, and you have people willing to invest money into the platform. Yeah, and therefore you have both of them, and they're independent of, or not really independent, but they are different things. Yeah. Is that okay?
Very good.